In this video, we're going to focus on the SN1 reaction mechanism. So let's say we have tert-butyl-bromide, and we wish to react it with potassium iodide. What's going to be the major product in this reaction? In order to draw the major product, all we need to do is replace the leaving group with the nucleophile. In this case, the nucleophile is the iodide ion. Now let's go over the mechanism for this process. You need to know that tertiary alkyl halides favor the SN1 reaction mechanism over the SN2 reaction mechanism. So the first step is that the leaving group leaves. The substrate is ionized. And because bromine is more electronegative than carbon, when that bond breaks, bromine is going to take the 2 electrons in this bond with it. And so we're going to get a tertiary carbocation and the bromide leaving group. Now at this point, the iodide ion will react with the tertiary carbocation, giving us this product. And so that's the basic idea behind the SN1 reaction mechanism. It forms carbocation intermediates, which means that rearrangements can occur. In an SN2 reaction, there are no carbocation rearrangements. For the SN1 reaction mechanism, it's a first-order nucleophilic substitution reaction. The rate depends on the rate constant K and the concentration of the substrate, but it does not depend on the concentration of the nucleophile. So if you double the concentration of the substrate, the rate of the reaction will double. If you triple the concentration of the substrate, the rate will triple. So it's a unimolecular reaction, whereas an SN2 reaction is a second-order nucleophilic substitution reaction, or a bimolecular substitution reaction. Uni means 1, bi is associated with 2. Now let's go over another example. Draw the major product for this reaction and show the mechanism as well. So let's react this alkyl halide with water. Water in this example can behave as the solvent and as a nucleophile. When the solvent behaves as the nucleophile, it's called solvolysis or solvolysis. In the first step in this reaction, the leaving group leaves. And so we're going to get a tertiary carbocation. And then in the next step, water is going to attack the tertiary carbocation. Now, it can attack from the top or it can attack from the bottom. Because it has 2 different ways in which it can approach the carbocation, we're going to get 2 different types of products. So we're going to get a racemic mixture of products. So we can get the water on the front, that is like on the wedge going out of the page, or on the dash, which means it's going into the page. Now, these 2 products are not equal. This one is the retention product because, as you can see, it's on the wedge as the alkyl halide. The other one is called the inverted product. So inversion occurred for this one. To get the inverted product, it has to attack from the back. To get the retention product, that means it attacked from the front. And now let's talk about this. So the bromide ion left, and so it's somewhere still close by to the carbocation. Now when water comes in, it can attack from the back, which will give us the inverted product, or it can attack from the front, which will give us the retention product. Now, there's nothing really stopping it from attacking in the back. Now, there is something that prevents it or slows it down from coming in the front, because when water comes in, the oxygen atom will be the one that's being pulled towards the carbocation. The oxygen atom has a partial negative charge, and so it's attracted to the partially positive, to the carbocation, or the carbon with the positive charge. Now, as water approaches, it's going to be repelled by the bromide ion, because the bromide ion has a negative charge, and oxygen has a partial negative charge, and so those two will repel each other. So due to that repulsion of the bromide ion and the water, we are going to get less of the retention product and more of the inverted product. It could be a 60-40 ratio, and in some cases a 70-30 ratio. You still get a mixture of these two stereoisomers. However, you do get more of the inverted product than the retention product. Now let's finish the mechanism for this reaction. So once water comes in and attacks the carbocation, we are going to get an oxonium ion. So basically an oxygen with 3 bonds and a positive charge. Now the last step is deprotonation. So we need to use another water molecule to take off the hydrogen atom. And so we get a tertiary alcohol. But keep in mind, we get 2 stereoisomers. So the OH group can be on the wedge, and it's going to be on the dash. So these are the 2 SN1 products that we get for this reaction. Now let's sketch an energy diagram for the SN1 reaction that we just went over. Now that particular SN1 reaction had 3 steps. So therefore there's going to be 3 transition states. The first SN1 reaction, where we had tert-butylbromide reacting with potassium iodide, it occurred in 2 steps. So for that example, we would have 2 transition states as opposed to 3. So just to draw a rough sketch for the first one, it would look something like this. This would be TS1, and this would be TS2. So for a 2-step process, you should expect to have 2 transition states. But let's focus on the last reaction that we did. So here we have the reactant, or the substrate, the alkyl halide. And then here's the second intermediate, which is the carbocation. And then after that, we had the protonated alcohol, or the oxonium species, where the oxygen had a positive charge. And our final product is the alcohol. So for a 3-step reaction, you should have 3 transition states. Keep that in mind. Now, let's move on to our next example. So here we have 2-iodo 3-methyl butane. What is the major product for this reaction? Draw the major SN1 product. By the way, the SN1 reaction occurs with the E1 reaction, but I'm not going to focus on the E1 product in this video, just the SN1 product. Now notice that we have a secondary alkyl halide, and it's adjacent to a tertiary carbon. Whenever you see that, a hydride shift will occur. So you're going to have a carbocation rearrangement. So in the first step, the leaving group is going to leave. And this gives us a secondary carbocation. And then here we have the hydrogen. And so the hydride is going to move towards the carbocation, giving us a more stable tertiary carbocation intermediate. And then the solvent is going to behave as a nucleophile, attacking that carbocation. And so we're going to have this product initially. So we have an oxygen with a methyl group and with a hydrogen attached to it. So this oxygen has a positive charge since it has 3 bonds on it. Now the next step is deprotonation. So we're going to use another solvent molecule to act as a base, removing a proton. And so our final answer is an ether. Now notice that this carbon is not chiral because we have two methyl groups. In order for a carbon atom to be chiral, it has to have 4 different groups. So therefore, we only get one SN1 product. It doesn't matter if we put the OCH3 in the front or in the back. It will represent the same compound. Now let's consider another example. So here we have an alkyl halide, in this case a secondary alkyl halide, that is adjacent to a quaternary carbon. If we react it with, let's say, water, what's going to be the major product in this example? Draw the major SN1 product. So in this case, since we have a secondary alkyl halide next to a quaternary carbon, a methyl shift will occur. But in the first step, the bromine atom is going to leave. And so initially we're going to get a secondary carbocation. And then in the next step, the methyl group is going to move towards the secondary carbocation. And so where the methyl came from, the positive charge will move to that position. And so now we have a tertiary carbocation. At this point, water is going to react with the carbocation. And then the last step is going to be the removal of a hydrogen. So now water is going to behave as a base, taking off this hydrogen. And so this is going to give us a tertiary alcohol. Now we need to determine if this carbon is a chiral carbon, and it is. It has a methyl group, an OH group, and this side is different than that side. The side towards the bottom has a methyl group. Towards the top, there are none. So because the carbon is chiral, we're going to get a mixture of stereoisomers. So we're going to get an unequal racemic mixture of these two products. And so that's it for this example. So watch out for carbocation rearrangements when dealing with the SN1 reaction mechanism. Now, here's another question for you. Consider these 3 alkyl halides. Which one is most reactive towards an SN1 reaction? Let me redraw this one. Put some space between the second alkyl halide and the last one. So which of these alkyl halides is most reactive in an SN1 reaction? So you need to know that tertiary alkyl halides are more reactive than secondary alkyl halides, and methyl alkyl halides are the least reactive in an SN1 reaction. In an SN2 reaction, the order is reversed. So here we have a secondary alkyl halide, and on this side a primary alkyl halide, and for the third one it's a tertiary alkyl halide. So tertiary alkyl halides are the most reactive in an SN1 reaction, and so that's what you need to keep in mind. So this one's going to be the best. Now let's consider another example. Can SN1 reactions work for primary alkyl halides? What would you say? In most cases, no. But there are some exceptions. For example, here we have an allylic alkyl halide. Primary allylic alkyl halides can work in an SN1 reaction. The key is the stability of the carbocation. The reason why normal primary alkyl halides like this one don't work well with SN1 reactions is because it's extremely difficult to form a primary carbocation. Primary carbocations are not stable, and so that's why this doesn't work in an SN1 reaction. The reason why tertiary carbocations are more stable than primary ones is because of the 3 methyl groups attached to the tertiary carbon. The methyl groups can donate electron density through the sigma bond, and so that is known as the inductive effect, and so they stabilize the carbocation intermediate. Another way in which a methyl group can stabilize a carbocation intermediate is through hyperconjugation. So on the right, here's a CH3, and then this is the sigma bond of the CH bond. And so this is the empty p orbital of the carbocation. And in the sigma bond, there are some electrons. And so these orbitals can overlap, thus stabilizing the carbocation intermediate. So those are the 2 ways in which a methyl group can stabilize a carbocation: through hyperconjugation, that is overlapping of the atomic orbitals, or through the inductive effect, where it's actually donating electron density through the sigma bond. Now, once the bromine atom leaves, we're going to get a primary carbocation. But this primary carbocation is stabilized by resonance. And so this double bond can move here. And so the positive charge is shared between 2 carbon atoms. So the key to the SN1 reaction in determining if it's going to occur or not, it really comes down to the stability of the carbocation. If we can't form a stable carbocation, the SN1 reaction is not going to work. If we can, then it will work. So for the allylic alkyl halide, because we can form a stable primary allylic carbocation, that's why the SN1 reaction can work for this example. Now, it's important to understand that the primary allylic alkyl halide can also undergo an SN2 reaction, because this alkyl halide is not sterically hindered, so both the SN1 and the SN2 reaction can work with it. But let's focus on the SN1 product. So once the bromine atom leaves, we are going to get a primary allylic carbocation. And then water is going to attack the carbocation, giving us an intermediate that looks like this. And then the last step is deprotonation. So we're going to take off a hydrogen atom, and this will give us an allylic alcohol. So typically, whenever you react water with an alkyl halide, you're going to get an alcohol as a major product, regardless if it's an SN1 or an SN2 reaction. Now let's try another example. So here we have neopentobromide. If we react it with water, will this undergo an SN1 or an SN2 reaction? Now we do have a primary alkyl halide. This carbon is attached to only one other carbon. And so primary alkyl halides do favor SN2 reactions. Now water is a weak nucleophile, and so that doesn't favor an SN2 reaction. Plus it's a protic solvent, which favors an SN1 reaction. Now the second factor that doesn't work well for the SN2 reaction is the fact that we have a quaternary carbon next to the primary carbon. And so because of this bulky group, it's going to generate steric hindrance from to the nucleophile. It's going to be hard for the nucleophile to approach from the back because of all these 3 methyl groups. So all of that steric hindrance provided by those methyl groups will reduce the yield of the SN2 reaction. So in this case, we're going to get the SN1 reaction, but it's going to be a little different. The SN2 reaction can still occur, just not in good yields. So keep that in mind. So anytime you have a quaternary carbon next to a primary alkyl halide, the yields for the SN2 reaction will be lower because it's sterically hindered. Now, In a typical SN1 reaction, the leaving group will leave. But if we do this, we are going to get an unstable primary carbocation. And so that's not going to happen. So here is what's going to happen instead. The methyl group is going to attack the primary carbon, kicking out the leaving group. And by doing this, we can avoid the formation of an unstable carbocation intermediate. So rather than getting a primary carbocation, we can jump to a tertiary carbocation. And so that's what happens in this reaction. I feel like I'm missing a carbon. Let's see, 1, 2, 3, 4, 5. I want to make sure I had that right. So now the water is going to attack the carbocation. Giving us this intermediate, and we know the final step is the removal of a proton. So therefore, our answer, we can draw it like this. So we only get one major SN1 product. And we don't have a chiral center, so we're not going to be concerned with stereochemistry. Now here's another question for you. Consider these 3 substrates. Which one works the best for an SN1 reaction? Feel free to pause the video. So notice that all of these alkyl halides are secondary alkyl halides. And on the right, they're all next to a primary alkyl halide. But on the left, it's different. Here we have a secondary carbon, here is a quaternary carbon, and this is a tertiary carbon. So right now, this is going to be the worst for an SN1 reaction. Even though they're all secondary alkyl halides, this cannot undergo a rearrangement. Now these two, they're very good for an SN1 reaction. This one can undergo a hydride shift, and this one can undergo a methyl shift. And so they both can generate a tertiary carbocation. So in that sense, they're similar. However, the SN1 reaction usually competes with the SN2 reaction. And this is terrible for an SN2 reaction because there's a lot of steric hindrance due to the quaternary carbon. So because the SN2 reaction is less competitive, this is going to be a better option. We should get a better yield for the SN1 reaction, even though both of them can lead to the same tertiary carbocation intermediate. So here is another question for you. I want you to determine which of these alkyl halides work the best for an SN1 reaction. So in the first example, we have an aryl halide, and here we have a vinyl halide. And then for this one, we have a benzyl halide, and this is another benzyl halide. So which one is the best for an SN1 reaction? So this carbon is secondary, this carbon is primary, this one is secondary, and this is secondary. So you might be thinking we could eliminate the primary carbon, and you won't be wrong for doing that. Now, you need to know that aryl halides and vinyl halides, they do not work for SN1 reactions or SN2 reactions. So we can eliminate those options. Now, these two, they have the same structure. Benzyl halides work very well for SN1 and SN2 reactions. So the real thing we need to look at is the leaving group. Which leaving group is better, the bromide ion or the iodide ion? If we look at the halogens, fluorine, chlorine, bromine, and iodine, we know that in a periodic table, as you go down, atomic size increases. So iodide is bigger than bromide. And iodide is the better leaving group because of that. Because iodide is bigger than the bromide ion, it can stabilize the negative charge better. If you can spread out a negative charge over a larger area, that process will be more stable than concentrating a negative charge in a smaller area. And so larger ions can stabilize a negative charge better than smaller ions can. And so for this reason, iodide is a better nucleophile, but a better leaving group than bromide, and bromide is a better leaving group than chloride, and fluoride is not a good leaving group. So leaving group stability corresponds with size. So in this case, this is the best alkyl halide for the SN1 reaction compared to all the other options that we have here.